Okay, welcome everyone. It's a great pleasure for me to welcome you to this first webinar of the series of webinars on control education organized by the IFAC Technical Committee on Control Education in cooperation with the IEEE Control System Society Technical Committee on Control Education. And it's a great pleasure for me to introduce John Hedengren, who is a professor at Brigham Young University in the Chemical Engineering Department, where he leads the Process Research and Intelligent Systems Modeling Group. His research interests include data science, machine learning, smart grid optimization, unmanned area systems, and predictive control. He is the chair of the Technical Committee on Control Education of the IEEE Control System Society, and we can say he is well known most of all because he has led the development of the Arduino-based temperature control lab that is currently used all over the world by more than 70 universities, especially for process control education. Before leaving the stage to John, I would like to announce you that the next webinar is scheduled on March 26th at 3 p.m. Central European Time, and it will be given by Steffi Knorn, who is the chair of the IFAC Education Activities Committee, and she will talk about controlled fun, teaching automatic control with gamification. So stay tuned. I will send you an email regarding the next webinar. But now, John, please, the stage is yours, and thank you very much for giving this webinar to us. The title is Data-Driven Engineering and Process Control Education with Portable Labs. John, please.
All right. Well, thank you, Antonio, and thanks everybody for joining as well. Many people that I know here that have joined, so thank you for coming, and look forward to your questions after this and comments and suggestions. Those are always very helpful. I just wanted to start with see if I can start with just an experience that I had a couple of years ago. This was during the height of COVID. I do some work on offshore platforms, and one of these in particular, it was the height of COVID. One of our fiber optic splicers, came down with COVID right before this trip. So I was basically had to do a lot of this project myself. Everything from the instrumentation all the way up through into the control system with the communications, the computer systems, the software installation, and it felt, I was out there for about a month. During this time, I really reflected on the things that I was teaching students and some of the importance of not only process control, but also be able to handle data, cleanse data, some of the data engineering aspects of what we do in order to be able to make systems work. So this experience really influenced my thinking in terms of how I teach, to give practical hands-on experiences to students that reinforce some of the concepts that are going to be very valuable for them when they begin work. And so I just want to talk today about some current trends in data and computing and some of the opportunities that it opens up for us as educators or industrial practitioners or students, some of the control education challenges as well. I'll talk about these portable lab hardware, both one that I've created, but also some of the community efforts in this area as well. And then some of the software that goes along with the hardware that supports these learning objectives, and we'll have a couple conclusions. So let's just talk first of all about data availability. A car that is maybe in self-driving mode is going to be generating 25 gigabytes per hour of data. A wind farm might be 150,000 data points every second, and a jet engine might be 51,000 gigabytes per hour that it processes to be able to assess health of that engine. And so there are many exciting new developments in cloud computing, in edge computing, to be able to process some of this data. And if we look at the current trends in data, we see that this is the number of zettabytes. Okay, so 1 billion terabytes. And if you think about maybe 1 billion laptops on the earth, each with a terabyte, that would be 1 zettabyte, would be all of that capacity. And so there's quite a bit of capacity in data centers and other ways that we're able to store and transmit this data. And you can see this exponential rise in the amount of data that we're generating and need to process and turn into actionable and useful information, not just to store it. So there's also been some significant advances in computing as well. This is the performance per watt that is typically looked at by large companies. How efficiently can they perform calculations per watt of energy used, which is often one of the key drivers in computing. And so you look at the CPU, which is benchmarked to 1, the GPU 2.9 times as efficient in terms of performance per watt, and then custom architectures like the tensor processing units that are 83 times as efficient in terms of performance per watt. And so we're seeing an explosion of new data that's available through sensors and cell phone cameras and other ways that we're able to transmit this data. And then we also see new computing architectures as well. This is just an example of some of the data or other things that might be available. You can generate some of these through simulations. This is a high altitude, long endurance aircraft that we worked on with Facebook or Meta, really before Starlink and some of the low Earth orbit satellites. The objective was this microgrid energy system that could fly at 60,000 feet continuously to deliver internet to all parts of the world. And when they had developed this to, perhaps have 10,000 of these flying around. And so as we embarked on this project, we think about data and we think about some of the practical aspects of control and automation. There's quite a bit that goes into these systems in terms of complexity, both from the physics-based understanding of what we know, but also in collecting data and using that to iteratively improve designs and the control systems. I mentioned cell phone cameras as well. Just with a cell phone camera, this is me running and then loading it into an app that I worked on that does AI form analysis. So with this, you can analyze an athlete's running form or some other type of movement. So I'm just going to load in this video and then let it process. This is a real-time process to do this machine learning on the running form and be able to pick out 33 data points on the body and then do some type of analysis on that. Okay, so here's my running form. I'm looking at hip drop in particular. It's a strong indicator of running injury. So all sorts of data sources, but also physics-based information that we have available. I'll just show one other example. I mentioned offshore platform work. Here's a simulator that's comprised of hundreds of thousands of differential equations that can be used as a surrogate for data if it's not available. And so, when students go out and start working, they're going to be exposed to massive amounts of data, a history of these physics-based simulators that have been developed over many decades. And so they want to be able to use these to be able to take their organization and provide benefit at the next level. And so with all of that in mind, I'll just highlight a paper that myself and others, worked on to really think about the control education societal scale challenges with the community roadmap. And some of the things that were mentioned here at a high level is that we really need to modernize control education, broadening the scope to include some societal scale challenges like climate change, sustainable agriculture, and biomedical applications. So increase, the theory and other things that we cover has such a wide-ranging impact in so many different industries, and to expose students to some of those. Also, one of the conclusions of this was to introduce control theory courses earlier in the curriculum, focusing on these real world applications. And don't start with detailed mathematics. Maybe do that in a later course. Okay, so hands-on, practical, really show them the enthusiasm for what you can do with control and optimization, some of these other methods before jumping into the mathematics. Also, a finding from this study was to modularize educational content and utilize open access resources, including virtual and remote laboratories, to enhance learning flexibility and accessibility. And then also, there's some case studies in this article that illustrated successful practices in control education, highlighting some of the use of hands-on practical experiences. And so the purpose of this presentation today is really to delve into what's been developed out there in the community and how can we use some of these modular learning exercises. So first of all, there are some commercial process control labs that are very good. You have software such as Control Station that has a number of simulation labs. You have Armfield. This one is PCT 40 with a number of process control experiments on it. You have Robot 5, these electromechanical breadboards that are very modular, that you can put things together, especially with mechanical action. You have the Quanzer, these little modular units as well, together with some very nice software, Simulink modules. And then, things like self-balancing robots or others that you can purchase off the shelf. So many good options there. One of the drawbacks to these types of systems is they're a little bit more expensive, and you typically have these in the laboratory and then students schedule time to come in and use these. So they don't typically have as much time during the semester, kind of one-on-one with these. And so that's where some of these open source portable labs fill that space, where you can give one of these to every one of the students and be able to have them use it throughout the semester, not just once or a couple times during the semester, but to really reinforce a lot of the concepts of the control class and make some of those mathematical concepts come alive with a practical application. So some of these are remote laboratories. Some of them are even frameworks, okay, for be able to leverage the data in this laboratory environment. Many of them are based on Raspberry Pi or Arduinos, or let's see if I can find any others. Here's Arduino. And so there's a lot of different microcontrollers that are available now that have enabled some of these labs at a low cost and portable way. Okay, a couple that I'll just highlight. Some have also just taken, these commercial toys like little drones, UAVs, and then have custom firmware that fits into those, basically to instead of as a toy, as a type of learning experience. Also, there are others in aerospace, for example, this little whirlybird or this helicopter lab that's a very constrained, safe environment to be able to learn some of these concepts. Also, a very nice paper that came out recently were the automation shields, and this is a collection of about 9 different experiments that you can use with an Arduino base. Okay, so the Arduino base, and then you put these shields on top and are able to run these different types of exercises. And many of these are 3D printed on top with some low-cost electronics and actuators and others that make these systems work. Okay, so all of those are posted online, and I have a link there if you'd like more information on that. One of them that we've developed is the temperature control lab. As Antonio mentioned in the introduction, many have used this one. We started in 2014, 2015, with this and have developed it. We've now produced 11,000 of those that have gone around the world to people in industry or academia to use these. Similar to the Arduino Shield or these, the automation shield ones. This is a shield that goes on top of an Arduino. And then as we go through our process control course, every assignment has some kind of a theory based, and then we have a hands-on with every one of the 23 assignments that we give as part of this class. So you have theory and then hands-on lab, and they can use it for every assignment, not just a couple times during the semester. And so at the heart of this is that you have a sensor and you have an actuator. Okay, so the sensor in this case is a thermistor that measures the temperature, and that is this orange line right here. And then an actuator, and this is just a BJT transistor that works as a switch for pulse width modulation, but also to be able to generate heat as well. As you flow current through that BJT, it heats up. And so here's your heater right here, and then your temperature sensor right here. And then you put two of these next to each other to give a simple multiple input, multiple output system, where as you heat this one up, this one feels a slight effect as well. Okay, so two transistor heaters, two thermistors, and just an LED that indicates when it's, it could be too hot to touch or blinks for some other reason. Okay, so we talk about programming, because one of the things we did is, first of all, start off with MATLAB, but then have since moved to Python for a lot of our control exercises. You can see the history of computing. The programming languages and those that are most popular change over time. So you can see C coming here, and then is the advent of really the .com period. A lot of the web programming languages really took off, and then you can start seeing Python right here as it rises, and the popularity of Python now is really ubiquitous through web programming, through scientific computing, and others. And interestingly enough, MATLAB has also risen during this time as well. So it isn't that Python has diminished MATLAB, but both have risen together, I believe, as scientific computing and process control have really become more popular and useful in this automation era. Okay, so what we've done is taken this lab, and then throughout the course, as we give them, for example, just do a step test and fit something like a first order plus dead time model, or create some physics-based models, okay, where we're modeling the convective heat transfer, the radiative heat transfer. We have it then a nonlinear model, but we don't have transfer functions. Now we need to get that back into a form that we can start working with it with some of the control theory. So we then have a lab on linearization, and we compare the nonlinear data to the linearized model, for example. And as we go through it, we do some graphical fitting. We then do regression. So not just with a step test, but maybe with a doublet test or some type of PRBS or other type of signal, and then we do regression. We also look at control design as well. And this temperature control lab, then every time they're going through these exercises, this isn't a new simulation or a new application. It's the same one that they go back to. So that doesn't become an obstacle for their learning. We then get on to P-only control. We introduce the integral and then derivative as well. And so those are the first 10, and then we go through with more topics as well. Okay, so these are the topics and how I've taught the course. I typically have between 70 and 110 students in the class, and so each of them has one of these temperature control labs. They take it home. They work on their assignments. They're working with real data that they generate throughout the course. Okay, so this is a little bit about the programming and how they control it. Also shows some examples of how to connect it with Simulink and MATLAB and some of the flow sheeting that's very valuable to show block diagrams, for example. But at the core of this, you're changing the heater values, okay, and then measuring the temperature values. And this opens us up, just these four commands opens us up to do many different types of process control exercises. And I'll show a couple in machine learning and data science as well. Okay, so here's some multivariate control. Okay, so this is it in MATLAB. Um, T1, T2 for the two temperatures, and then Q1 and Q2. And so in this exercise, they're trying to maintain set points for the two temperatures by adjusting the heater values there. So it's a multivariate control system that runs through MATLAB or Python. All right, so this is, for example, building the Simulink interface. I'll just fast forward through this, but it shows how the signals come in and then how they build this model to then translate those voltages into temperatures and then also be able to actuate the heaters as well. Okay, so once they have that, this is an open loop simulation. So if we want to go to a closed loop system now, we'd remove the sliders here and then now put a PID controller in here instead. So this shows the Simulink. I'll change this from a heater 1 actuator to a temperature 1 set point. So now I'm defining a new objective here, which is, okay, I want to be able to maintain that final temperature. And I'll change some of these. I should have fast forwarded this a little bit faster. I'm going to go forward just a little bit on this. Okay, so I'll get the PID controller. I'll put that in here. Okay, and then I'll break some of the connections and then put my summation in here. Okay, so you can see one of the exercises here is for the students to take this and build their feedback control system to be able to take their temperature fed back into compare with a set point and then a PID controller that then actuates the heater value. And then we'll go ahead and just move some of these signals around just so that we can see the set point, the temperature, and also the heater value, all three on one of the scope plots. Okay, so that's, as we go forward on this, you can see that then the student runs this. They've taken an open loop system, transformed it into a closed loop system, and then they run through this lab to be able to tune a PID controller. Okay, the other thing that we've worked with MathWorks quite a bit to develop these live scripts that make them very interactive, where you can have slider bars, move things back and forth, and see simulated. So it walks through. Here's a simulation of the lab. You get approximate tuning values, and then as a final step, you then run it on the actual device, all within the same live script. So it's a very nice alternative to running it in Simulink or with MATLAB scripts. These live scripts add a bit more of interactivity into the learning exercises, and we appreciate the support of MathWorks in helping to develop these for all the modules. Okay, there's also things like auto-tuning PID controllers, and I'm not going to show this one, but in some of my other videos on this, you'll show some demonstrations of even like auto-tuning and other capabilities. Okay, so many different types of models that are in control theory. We typically, in our introductory class, we focus on like a first order plus dead time model. state space and transfer functions together with linearized physics-based models, okay, or just nonlinear physics-based models as well. In industry, for advanced control, they typically use FIR, ARX, some state space, and some of the newer companies like Immubit and others might be using LSTMs. And so those are some of the ones that are used typically in industry. But we have some newer ones, for example, transformers, same things that power ChatGPT or Copilot with GitHub, Microsoft's Copilot. So some newer models that are also available, physics-informed neural networks or hybrid models. And so with these labs, one of the things that we're attempted to do, I'll show just a quick demonstration of those, is that every time there's a new model, then we use the same type of data, the same system, and then just see if we can control or simulate the system. So it becomes like a benchmark problem that as we develop new models or new methods, things that we want to teach, the students can always go back to the same application that they already know really well, and then it becomes like a benchmark. Well, how well did this perform relative to other models that I have in my toolbox? Okay, and so we also have some in our advanced control class for dynamic optimization and model predictive control, do other exercises such as moving horizon estimation and model predictive control with this same one. And then it helps the students visualize some of these more advanced concepts where they're using some of these other types of models and creating predictive applications that see forward into the future. You could see that here with the future MPC and then the learning that happens with this moving horizon estimation as the model adapts and the parameters change as it learns the dynamics of the system. Okay, so on to just a couple more examples as well. This one is an OT cybersecurity, and as opposed to IT, operations technology are things associated with like the equipment in plants that are pumps and valves and other things. There's quite a big cybersecurity push in this area to do things like, if somebody has access to your system, how can you detect them? And they might be just making small changes to your system. So think of like Stuxnet or other cybersecurity instances where somebody had remote access to the system. They were making small changes over time to either reduce the economics or damage the equipment. And so this is an example of how we've used some of the temperature control lab data or some other fabricated data to generate scenarios to be able to detect these types of intrusions. So helping these types of applications come alive to the students through these hands-on learning environments. And so this is one example here. Here's our heater values right here, and then our measured temperature, and then these are the derivatives of our temperature. What we're trying to do here is to be able to detect when the heater is on or off without knowing if the heater is on or off, using 8 supervised learning methods and 3 unsupervised learning methods. And so the students get experience with all of these machine learning methods for classification to be able to detect things like, I'm commanding my equipment to do this. Is the equipment really doing this? Okay, and so be able to detect if there's a difference between what I've commanded and what the machine is actually doing. Then it can be one of two things. Either the equipment is broken or somebody has control and is spoofing what I'm seeing through the interface. So as an OT cybersecurity exercise, we're also using this portable lab to reinforce some of these concepts in machine learning. So let me talk just briefly about machine learning and how this has influenced how I teach and some of the trends that are happening. So we've talked about these hands-on laboratories. uh, a very nice speech by Salman Khan, who does Khan Academy. He mentioned this study that shows that as we adjust the student to teacher ratio, okay, there's a certain summative achievement score that students are going to get on average. And maybe this is how we teach our classes, one teacher to 30 students. And here's the distribution of summative achievement scores. Maybe the average student is going to get a B, and then some of them will be above the A mark, and this might be our C mark, okay? And as we do mastery learning, that can be active learning or more advanced teaching strategies. We see that we push this distribution to the right, and so back here, and then as we get to one-on-one. So if you could clone yourself, and for every one of those 30 students, and work with them individually, that would further shift how much students learn dramatically. So now your average student is equal to some of your top performing students before, and your lowest students are equal to your average students from before. So what can we do with AI to really enhance some of this one-on-one tutoring and not take away from the educational experience, but to actually save it or enhance this learning experience? So as educators, I'm sure all of us are thinking about what to do with these new technologies and how we can enhance the learning instead of detracting from it. So one of the things that I have here is this lab companion for the temperature control lab. So this is a tuned GPT that is specifically built for the temperature control lab and other hands-on labs to help walk them through some of these exercises to help them get started. So here's a question that I asked it. How do I upgrade the TC Lab Python package? Okay, and it gives me two methods for doing this. Here's one, just pip install TC Lab, and if you need to upgrade it, use the -- upgrade. Or if you want to get the very latest one from the GitHub repository, then do pip install from GitHub directly. So that was a correct answer that it gave. And then I gave it a slightly more challenging one. I just took a picture and uploaded this photo. I said, why doesn't the heater get hot? Okay, and so in this, it identified if the heater in your TC Lab is not getting hot, it can be due to an issue with how the device is powered. Okay, it requires two connections, one to your computer, another to a separate power supply. If you only have connected the device to your computer, using a single cable might not provide sufficient power to heat the heater. Ensure the device is properly connected to both computer and additional power supply. And later, as I went on, I continued to ask it questions. It identified that this was the correct place, this power plug 1, and identified those characters and said, hey, you need to plug in your power cable there. So it did a very good job, even with the photo and a very simple prompt here, to help troubleshoot, why this heater wasn't getting hot. Okay, so as we think about generative AI in education, in some of my teaching, I found that, I'm able to help students with this foundation, but then they quickly get beyond that because of this assistive nature of the generative AI to start tackling more challenging problems in this realm of creating, evaluating, and analyzing. And as we see in business, some of these, like what happened, is at a low level of synthesis, okay, or reports, or this dashboarding or other things where you take data and you say what happened versus what will happen next, or what is the best that can happen. And so we want to drive students to be thinking at these higher levels in terms of forecasting, statistical analysis, and optimization, predictive modeling. And so one of the roles that I see of generative AI is getting beyond some of these base level items, that often correspond to the understanding and remembering up to some of these higher level aspects of learning where they're creating, evaluating, and analyzing. Okay, and so going back to my experience on this offshore platform with some of this, data pipelining, data cleansing, just some of the raw nature of working with these systems and sensors directly, I think there's a lot of value in this data-driven engineering concept. In addition to what we teach a lot of times in process control, engineering programming, optimization, maybe even machine learning, really a foundation for a lot of it is in this data-driven engineering. So I have a few modules here, that worked on also with these portable labs that reinforce, how to import, text data, video, databases, sensors, cloud computing, web scraping. All of these are part of this, be able to handle data, work with it, import it from different areas, store it, which are critical components of how people work today. And then also how to transmit data as well through this older Modbus technology, MQTT, which is really for Internet of Things, OPC UA, that is a common communication protocol in industry, or web programming, such as WebSockets or other standards for high speed and reliable two-way communication. Okay, so one of the things I've started doing as well, and is that I've started using more modular labs that students can just build themselves, like from an ESP32 or an Arduino device. This is an ESP32. It includes a Wi-Fi chip, Bluetooth as well. And then we just connect these sensors, like the BMP 280, to give air pressure. And so one of the things that I've done with this one is I've given them this device and then this correlation here. And I tell them, hey, take this sensor around, maybe drive it around in your car, and measure the elevation difference based on the pressure. So it's sensitive enough to get elevation differences of about 3 feet. Okay, and so this is an example of a map that is generated as students go around and they collect their own data, and then they analyze it in the context of data-driven engineering with cleansing and transforming it into elevation, for example. Okay, so I'll talk just briefly about machine learning as well. I've spoken about process dynamics and control, data-driven engineering, and then machine learning is another area that a lot of students in process systems engineering, the fields that we teach, are very interested in right now. And so adapting some of the software concepts to this area as well. So we use machine learning almost on a daily basis. Our cell phones, fraud detection when we get those notifications about a purchase that was made, our email and spam filtering, speech recognition, image recognition, etc. And I believe these tools are going to become even more pervasive in our lives. And so as engineers, as instructors, teaching students not necessarily become machine learning engineers, but to become process control engineers, or engineers with machine learning understanding and capability in their tool belt. And so these are some additional modules similar to the process dynamics and control course. This flow chart of how I've taught the machine learning class on this area up here. We're on the data cleansing, scaling, using physics-based digital twins, consolidation, feature engineering, data visualization. And then once all of that is done, more on the data engineering side, okay, then we get down into what we traditionally call some of the training or fitting process with machine learning, where we split into these three train, validate, and test. and then either perform unsupervised or supervised learning with classification or regression. Okay, so portable labs also have a big role in reinforcing these concepts as well, just like the process dynamics and control course as well. There's going to be additional tools that we're going to use, different packages to be able to do the regression or classification exercises. And these are some of the popular machine learning packages that are in Python. Also, many of those same ones are available in MATLAB as well. And then looking forward to the future, we think about some of the models that we use, maybe linear, ARX, FIR, it might be FOPDT models as well. And as we've seen things develop with machine learning, and we've seen really the start of transformation in natural language processing due to the transformer. I'd just like to pose that we might be seeing a similar transformation also in process dynamics and in modeling, time series modeling as well, using this same transformer technology. And so some initial studies have shown that, as we use LSTM or transformers here for our prediction model, we can hook that to optimizers and then be able to have improved model predictive control that does a better job than some of the traditional methods for modeling these systems. We can also use physics informed, so a blend of the physics-based information, where we put the physics-based model here together with the data-driven model. And so it doesn't become an either or, where we either throw out our physics-based information or throw out our data and use, it's a combination of the two that gives us this combined objective function or loss function. And so as we look at the temperature control lab, again, this benchmark for these different methods, here's our temperature one that we're trying to model. And this one is actually an LSTM model, but with physics-informed information. We see that we can train it on this information, and then this becomes our evaluation in this area right here. And so with physics-based information, it really helps it extrapolate to new conditions. And so I'd suggest that as we start thinking about adopting some of these new models and new methods and even ways to teach it, it would reinforce this concept of it isn't just about the data. We need to often include physics-based information in our features or in the methods themselves to be able to help it extrapolate and generalize. Okay, I'll just mention briefly some teaching resources as well. This is a collection of pages. I help maintain the process control and computer programming. There's also an optimization one now. And so these are some of the teaching resources, where you're collecting links and curating content for instructors to use in an open source way. Also, Brian Douglas has created this resourcium.org, and this is an excellent website for collecting and curating content, especially about control. So I highly recommend that if you haven't been onto Resourcium. Just like to thank some of the TC Lab collaborators who have done great work to make a lot of this material available, not just the hardware, but also a lot of the software modules. And then also for the machine learning course collaborators, I couldn't have done this without the help of these fantastic individuals who have helped to translate some of the content into MATLAB and these environments to give these interactive modules. All right, well, that's our presentation. Thanks for your attention, and I'm glad to take any questions as well.
Thank you very much.